Professor Micharet is the Associate Professor in the Department of Systems Engineering and Automation at University Carlos of Madrid. I hope that's correct.
Yeah.
um, she received her PhD degree in industrial engineering from the University of Extremadura. And, her work is really on controllers for flexible manipulators and soft robotic links. And she has been awarded with the European Doctorate Distinction Award and the Doctorate Extraordinary Award. So super excited to see what you have to tell us about today. Thank you.
Okay, thanks a lot. Okay, I will share my screen. I have to, sorry, but I have to select here only the host or all participants. I mean, this is asking me to select some options to share my screen.
I think for all participants would be guess. I think you're on host options. Maybe try not the little up arrow, the main share screen button.
Share screen, okay.
There's a big red or green share screen button.
Oh yeah, sorry. Okay, great, I have it.
Thank you.
Okay, you can see, thanks a lot. You can see now my presentation, right?
Yes.
Okay, thanks a lot for inviting me to share these research with these amazing audience and amazing presentations. I am presenting the research we do here in the robotics lab in the University Charles III, Carlos III in Madrid, about soft joints for robots, right? And this is a very short talk. There are many things to comment on, but I will be very brief in my presentation later. Of course, if there are questions, I will be happy to answer. But the idea here is we have a humanoid robot. And as you may know, working with humanoid robots is quite difficult because of the rigidity of the human body of the robot, right? And we are trying to replace certain parts of the robot by soft joints. So the idea here is to replace the neck mainly, and then the arm. And in this design procedure, we have thought of a particular type of a joint which is useful for both solutions, right? For the neck and also for the arm. So I'm showing you here the evolution of the design, the modeling, and the control of these kind of joints, right? So the thing is that even if this is a very complex system, we are linearizing it. We are considering it as a linear time invariant system. So in order to simplify the model, and then later we will design a very robust control. This is our topic here. And the type of controllers we use are called fractional order controllers. We will see later what they mean, right? So this is the thing. So what we propose here is this kind of a design in which we have clearly an elastic beam here that we actuate with the help of 3 tendons, right, connected to motors that we have here in the base. So according to the actuation of the motors, we can change the length of the cables here, of the tendons, and it will cause a movement, a change in the orientation and the inclination of the platform. So these elements here that you can see at the tip are to allocate different masses, loads, so that I can measure the robustness of the system when different loads are placed on the tip, right? This is the idea. So we are working with a 3 degrees of freedom soft continuum link, as you can see here. We, of course, at the very beginning, we tried to use steel springs. We forgot about that because they are not really soft. So now we are working with Ninja Flex materials and other materials. Particularly, this prototype is made of, this beam is made of Ninja Flex. And as I told you before, even if the system is non-linear because of the materials, and also because we are adding different loads and we have gravity effects, we are simplifying all this a lot, right? And even if it is a strong simplification, as you will see now, we will see how effective our controllers are, right? And this is the thing we have to remark here. the control part more than the modeling part. So what we do, just for you to simply understand how we modeled the system, we just simply actuate on one tendon, right, with an input that you can read here, which is a neck inclination. This is an inclination, a step of inclination for the neck. And this is the input signal to the system. And as output, we measure the neck inclination with a sensor, with an inertia measurement sensor or unit, right? So according to this relationship, output input, neck real neck inclination and input inclination, we measure that dynamics and we identify that as a first order system. I understand, I totally agree that this is extremely simple, but this is for us a good thing, because even if the system later is more complex than that, we can demonstrate that in practical experiments, the controller works perfectly well, even if it has been tuned for this simple system, right? We will see. So we identify the system with K and T, a simple first order system, having this bow diagram in frequency and having also this step response. So we can see that for that step of inclination, the neck reaches that particular inclination that we have here, right? So according to this, we design a controller for that system, simple system. So the thing here is that that controller must be robust to certain aspects, mainly changes in the mass of the load. We are using different loads to demonstrate that the controller is able to fulfill stability, but also robustness. And I will describe later what we understand by robustness here, right? What is the thing here? Of course, if we change the mass at the tip, we are changing the dynamics. This is quite clear, right? But also when the positions of the motors, the pulleys are changed, it implies that also the distribution of force and the velocity from the actuators to the soft continuum mechanisms, they are changing too, right? So we have to take that into account, and also that we are using rapid prototyping here. So we will have some mismatches from one model to the other, right? So we have to design a controller able to face all these mismatches and uncertainties and simplifications we have done, right? So for us, we have three particular main particular control specifications, as you can read in the slide. So first of all, for that system, for that neck, which is moving, what I want for the neck is to move at a particular speed, right? Which is a condition that we can fix with this condition here of the open loop in the frequency domain, the gain crossover frequency, which has to do with the bandwidth of my system, with the speed, and also the phase margin, which is also affecting the damping of the system, right? So I want it to be that fast. I want this system to be that oscillatory or with this particular overshoot. These are the two main conditions, right? And the third one is that I want the system to be robust when the mass changes, when the load changes, right? So what we did, which is this third condition that you can read at the end of the slide, we have demonstrated that the changes in the mass they affect mainly the gain of the system, right? We have identified the changes in the gain according to changes in the mass of the tip, right? So we want then to guarantee that the controller is robust to gain changes of the system, right? So what we do here, this third condition is to guarantee that, and I will tell you, I will show you how this is affecting. Look, for a specific phase margin of this amount, 100 degree, which means I don't want oscillations for my neck, okay? And this particular velocity, 1 radians per second, which is quite fast, right, for the system, where I am guaranteeing when I achieve these two conditions, here you can see that we achieve 0 decibels at a frequency of 1 radians per second, and the phase margin is also 100 degrees. At the same time, the third condition is that the phase here, if you look at the phase in the bow diagram, it is flat. this is flat. So it means that if we change the gain of the system, making it higher or lower because of the mass, right, that we place at the tip, the phase margin is not changing. And this quality of the response is reflected in the temporal response you have in the figure at the right. So you can see that for different gains, the overshoot of the system keeps constant. And this is the robustness we want to achieve. Whatever the mass, the system will be faster or slower, but the overshoot of the system will be kept constant. So if there is no oscillation, there will not be oscillation for any of the masses I place at the tip. Okay, so here you can see, I'm going to cancel a little bit the sound of the video, but you at the right you can see how this controller performs when it happens. You can see that there are a lot of masses, right? We have some discs with different masses at the head, placed at the head of the robot through the neck, right? And you can see how the oscillations are totally cancelled, whatever the different mass I place at the tip. And this is the robustness. Of course, we achieved that. I didn't comment on this, but the controller we are using is this fractional order controller. It is like a conventional PI controller, can you see? But the derivative here, which is having negative sign, which means an integrator, right, is fractional. So we are not using integer orders, but fractional orders of the integrations, and it helps us to achieve this kind of robustness property. So of course, we don't have time to develop all this theory, but these kind of controllers allow us to reach this type of behaviors. And we have also, implemented this kind of control in a new, based on the same philosophy, right? Based on these type of designs actuated by tendons, now we have developed this arm. This is a soft arm, and able to, again, to support certain loads at the tip, as you can see in the video at the bottom of the slide, right? And you can see how now the tendons are inside the structure, so that structure, the system itself is safer, right? And we can see how we can reach with not very powerful motors, right? Amazing bending, I would say. You can see at the top video how this is bending a lot, right? So we are quite proud of this, and we are under a patenting licensing process of this technology, right? Also, we don't have much time, but I would like to also show you some results we had using instead of inactive or passive tendons, using SMA, shape memory alloy actuation. So each of the tendons here are now active. I don't know if you are familiar with this type of materials. Shape memory alloys are able to elongate or contract according to the temperature, and we fulfill that giving a particular current for those actuators. So according to or controlling the currents in this type of actuators, we can control the length of the tendons, right? And here you can see for different steps of movements, we are achieving different inclinations. And even if the system is slower because of the action of the SMAs, the system is totally robust in absence of load and with a load of 1 kilograms, right? So we are also happy with these results. And just to finish, we are increasing the type of joints, or working on different type of joints, soft joints. And now we are developing an origami-based soft link with 1 or 2 even tips or links connected, and even more, right? So here you have some examples on how this paper-based or origami is able to support certain loads working correctly. and in a robust way, also because of the design of fractional order controllers. So we are now developing these kind of structures and also combining the previous links I showed you before with these links so that we can combine compression through the origami, but also inclination and orientation through the soft arm we have explained before, right? So this is all. Of course, I will be very happy to answer your questions in case you have questions at the end of the session. Thank you very much.